Well, so Piotr Mormul from University of Warsaw, and his talk is Nilpotent approximations in the Goursat monster tower. Piotr, please.
Yes, thank you. Thank you for accepting my talk. And let me start by recalling, by saying something's very, very sad, that scientists, including several mathematicians, physicians, were already killed over the last 3 months already. So I think this talk is devoted to today's memory. Thank you again for introducing me. And so I'm continuing my traditional subject. In fact, 1 year ago, I had a talk consisting of 2 problems. Oh, sorry. So, in fact, I'm dwelling on my second problem from the AGMA 2021, and again commenting to Professor Telemann. In fact, my methods are algebraic and geometric, being applied to analysis. So it's really a mixture of algebra and geometry being applied to analysis understood as non-holonomic analysis. That is analysis on a manifold endowed with a completely non-holonomic distribution, sub-bundle in the tangent bundle that generates all directions after Lie multiplications many times. And the number of Lie multiplications may, of course, depend on the point, but eventually one should end with the full tangent bundle. So this is completely non-holonomic object, sub-bundle distribution, geometric distribution living on a manifold. And the whole theory is about non-holonomic analysis. So, in fact, all definitions are in that paper that is mentioned here. This is quite an old reference, so 17 years already. And when I'm talking about algebraic methods, I'm thinking about Lie algebras, and mainly, predominantly about nilpotent Lie algebras, finitely dimensional Lie algebras, nilpotent Lie algebras, related or associated to completely non-holonomic structure, that sub-bundle completely non-holonomic. And the 2 very important notions are, the key notions for my talk are just strongly nilpotent points on manifold endowed with such a structure, and tangential points. Both notions are defined, as I mentioned, in this short abstract, but I'm going to recall the definitions, okay? So one more thing. In fact, last year talk had the title, after comma, in quest of a coworker, in quest of a coworker. So that quest is still actual. I'm still looking for a coworker, but anyway, I'm going to report on some progress, not dramatic, but some progress. So let me start with just recalling the 2 basic notions for my domain. So weak nilpotency, and in a moment of a point on a manifold endowed with such a complete non-holonomic structure, and then in a moment strong nilpotency, okay? So my talk will be full of codes, of labels, so words over alphabet RVT, R for regular, V for vertical, and T for tangent. So please don't be afraid of many codes over the alphabet RVT. And also I am going to extensively use the growth vectors, so the sequences of natural numbers, non-decreasing sequences related to derived flag of a given sub-bundle of a given distribution. For instance, here we have a distribution spanned by D linearly independent vector with tangent to the underlying manifold. So such an object, of course, generates its derived flag. So very classical object. And the sequence of linear dimensions of members of the right flag, this is big growth vector, BGR, in what will follow. And also, apart from the right flag, also in use, probably even more important, is so-called Lie flag or weak derived flag of a distribution, geometric distribution. So a sequence of linear dimensions of members of Lie flag or weak derived flag, that is small growth vector of D at a point. And in abbreviation, it is SGR. So please don't be scared by many BGRs and SGRs. So coming to the point. So weak nilpotency, very important in non-holonomic analysis and also in applications in robotics, in mechanics, in steering, in moving steering problem, moving objects on manifolds, so in space, subject to some restrictions. This is the following notion. So the point on a manifold is weakly nilpotent when this local representation of distribution admits certain visualization generating nilpotently, in fact, nilpotently algebra, always finitely dimensional. So it's not automatically clear. One may have distribution represented locally by collection of vector fields, absolutely not visible whether such a distribution is locally around a given point weakly nilpotent or not. But sometimes it is, not very often, but in my cases often, but in general not often. And let me just say that the word that I'm going to present to recall you is the word of Goursat distributions. That is very special objects, in fact rank 2, so D is 2, but such a subbundle, two-dimensional subbundle, tangent bundle should span, should generate, should be completely holonomic, should generate the full tangent bundle, but very slowly. So Goursat, D is Goursat when its big growth vector, that is to say the sequence of inner dimensions of its derived flag, grows very slowly, regularly. This is classical. This goes back to the end of 19th century. So it starts with rank 2 and then 3, 4, 5, up to the dimension of manifold. At any point, at every point. So very slow, very regular growth of the big growth vector of the sequence of dimensions of the derived flag. So this goes back, as I told, to Engel and to von Weber at the end of 19th century, and then to Elie Cartan, 1914. And Goursat was just making publicity of the results of the dimensioned man. So weak nilpotency is basically recalled, I hope. Let me maybe show you that this very classical word, this Goursat word, has, just to make clear where is the problem, it has a nice visualization, kinematical visualization. Maybe some of you have listened, have watched that already. Namely, very, very idealization, car towing or drawing number of trailers, passive trailers. So two-dimensional visualization, but several trailers, so a lot of angles. So in fact, this kinematical visualization is for Goursat. The underlying distribution, two-dimensional distribution is Goursat. You can steer by moving the car forward or backward, or by turning it. So you have two controls. So rank 2, underlying distribution on the configuration space. And that distribution is Goursat and is locally universal. It is a locally universal model. But the description is so completely strange, or it uses trigonometric functions. Yes? So a lot of sines and cosines. and one absolutely is unable to see whether this visualization curve is locally weakly nilpotent or not. And it was Hector Sussman, so the important man in geometric control theory and robotics and differential geometry also, Subrimanian geometry, very important. So he asked the following question, exactly whether the Goursat objects, the Goursat distributions, whether they are weakly nilpotent or not. He used the notion nilpotent, but his nilpotency is weak nilpotency for my considerations, okay? So his question being asked, you see, 98, last century, and I answered that question only in 2 more years, in the year 2000, in the affirmative. Yes, so Goursat objects, all of them, living on all stages of that horrible monster, Goursat monster that I'm going to recall. So all points on all stages of that monster tower are weakly nilpotent. So it's possible to locally find such a nice basis generating over numbers, not over functions, nilpotently algebra, which is absolutely non-visible in kinematical presentation, and which sparked the Hussman question, because that was not the trivial question. And you see, it took 2 years to answer that question in the affirmative. So let me now recall the strong nilpotency. Strong nilpotency, this is notion so-called proposed by myself in that year 2000, which is something very, very, in my opinion, very important for non-holonomic analysis. And this is apparently also opinion of Andrea Grachov and several other researchers. And namely, distribution is strongly nilpotent at a point when its nilpotent approximation is, let me show the very definition, when its nilpotent approximation is equivalent as germs to the germ of the initial object. So this is the germ of the initial object. So the germ of distribution D at the point of manifold, and this is its nilpotent approximation. But sometimes, instead of this notation, one uses the following notation. So all generators, all vector field generators are being nilpotentized, and this way of writing or this, they are just different ways of saying, of declaring the same. So let me start some more essential information from the very beginning information, observation. But strong nilpotency is really more strong and implies weak nilpotency naturally. The reason is very natural. So, well, for those who are somehow introduced to the subject, it's obvious, but it is just one line explanation. But it is not the other way. Of course not. And that is the beginning of the story that started, in fact, during my discussions with Andrei Alexandrovich in the year 2000. Namely, I proposed, he was kind enough to invite me to test, and I produced in his office the following example. So this is, by the way, one of Goursat objects in dimension 6. You have the first generator, the very simple generator that is in the local coordinate 0, 0, 0, 0, 1. And the second and last generator, one uses 6 variables, okay? So this is vertical way of writing these objects. So the Goursat condition is satisfied, that is to say, big growth vector at every point is 2, 3, 4, 5, 6. But it is not so for the small vector, which is slower on a submanifold described by x6 equals 0, and in particular at 0. So that small growth vector, that SGR, is 2, 3, 4, 5, 5, 6. It slows down here, in codimension 1, but in particular in 0. So let me briefly recall the procedure of computing nilpotent approximation, because it is essential for all that will follow. And in fact, the main actor or important actor was André Belaïche, the French mathematician. I'm not sure whether he is still active, but he proposed very nice algorithm towards the end of 20th century of computing, of producing nilpotent approximation of a given distribution at a given point. So I'm applying his algorithm. I forget maybe these horrible expressions, but this is application of his algorithm to this case. And the result is the following. So I'm passing from the variables x to variables z, his typical adapted, so-called adapted variables, okay? So after passing from x's to z's, the description of first of this simple generator doesn't change, but the description of the second generator changes substantially, and I'm separating the most important terms, so-called quasi-homogeneous weight -1 terms, and I'm rejecting, just leaving some other nested terms that are, in this case, of quasi-homogeneous weight 0. So they are not necessary. The nilpotent approximation uses only quasi-homogeneous weight -1. So the result of applying Belaïche is the following. So an A for nilpotent approximation of the object in question, okay, is the following. And you see what is a fantastic result. Only two first z variables are in use, and this has immediate consequence, but I'm going to skip details, but this corollary, this consequence is really elementary, believe me. Namely, the big growth vector, the BGR of this nilpotent approximation appears to be the same as the small of the initial object, of the small of this object, and that is the same as the initial object, because the small growth vector is being preserved in passing from initial object to its nilpotent approximation. This is basic property of NAs, of this functor, in fact, of passing from distribution germ to nilpotent approximation of that germ. So SGR is being preserved. And here I'm stating, thanks to these two variables only, that the big growth vector of this newly produced object is the same as the small. And the small is the same as that of the initial object. That is to say, the BGR of this produced is this one. But of course, this is not a Goursat big growth vector, because for any Goursat in dimension 6, that would be 2, 3, 4, 5, 6. So with having this object having different big growth vector than Goursat, of course it is not Goursat. Of course it is not Goursat. So this is the first example, let me recall, the first example that was kind of a surprise for Andrei Alexandrovich. Here we have in small dimension, relatively small dimension 6, the object that is not strongly nilpotent, but weakly nilpotent. Of course it is, because the whole Goursat monster tower, including the level 4 in dimension 6, is weakly nilpotent. So let me pass to some more interesting example. And in fact, recalling now the very problem I'm talking about. This problem is to tell strongly nilpotent points from all points on Goursat monster tower. All Goursat monster tower, that is to say, all levels. Here we had example in level 4, dimension 6, but all levels are weakly nilpotent, and only very few, relatively few points on those levels are strongly nilpotent. And in my opinion, attempting to answer the question which points of G and T, Goursat monster tower, are strongly nilpotent is quite essential. It is important also for applications, not to mention that kinematical model, but to some other applications. Also, this is important. So one more example, okay. Again, in this example, I'm using so-called brute force, so applying Belaïche. And the object is, again, as I warned you, so one is going to see sequences of letters, so words over alphabet R, B, T, R for regular, V for vertical, T not yet visible here for tangent, but it will appear later. So in level 5, one level up in this class, which is also all points, that is to say, all points in this class are not strongly nilpotent. And here is the short explanation. So the initial description, so-called Kumpera-Ruiz description. So these X's are Kumpera-Ruiz coordinates, very classical in this stuff, probably well known to those of you who listened to me on several previous occasions. So let's fly over Belaish in this case. So the small growth vector is much more complicated already. It is like that, like this. So you see how slow it is. While the big is 2, 3, 4, 5, 6, 7, every point. So small, slow substantially. And then some weights essential for computing nilpotent approximation. These are written in red. And at so-called adapted coordinates of Belaish, passing from X's to Z's. And the result, the outcome of Andrzej Belaish procedure. But one doesn't see much, as I mentioned, as I wrote here, yes. And one should do some more trick. One should pass from Belaish adapted coordinates to so-called super adapted. This is a local invention important for this tower, for this GMT. In this super adapted, you see in a moment the outcome. The nilpotent approximation assumes a fairly elegant form. No longer only two active variables, in this case 3, Z1, Z2, and Z3, but the role played by Z1 is very particular. You see, this is the versor of Z1 variable. So when you multiply the first and second generator, this Z1 disappears. And so here is the result of computing the first least square of this nilpotent approximation. Okay, so this is the least square. You see, I'm multiplying this object with itself. And because of this very particular appearance of Z1, the outcome is up here, is down here, sorry. So Z1 is no longer visible. One more generator, of course, adds up. You mean this, differentiating this gives you 1 here, and you can subtract. Yes, you can subtract so as to write the generators of this least square in more elegant form. Here they are. And now you see the previous situation. Well, this is somehow indicated in red. This is the previous situation. So, but one extra passive vector generator. But based on the previous computation of that very first example from the year 2000, that was so surprising to Andrei Alexandrovich. So we immediately see that this least square has this big growth vector. The previous one plus 1 at each entry, yes, because of this passive. Okay, so before performing this least square, before we have not this big growth vector, but this one with initial 2 put in front of this, yes. So again, this big growth vector of the nilpotent approximation in question is bad. It's not Goursat. It's not Goursat. So second, not strongly nilpotent example. Yes. Let me skip this remark. This is technical remark, important in some sense, but let me skip it for a moment. And now we come to the main, how to say, improvement or medium-sized improvement over my previous attempts. By the way, the problem is still open. It is, as I mentioned in the abstract, what I'm proposing is a roadmap. It's a roadmap to completely solving the problem, that is to say, to completely indicating, pointing precisely all strongly nilpotent points in the Goursat monster tower. It is not yet done, but the answer is well understood by myself, but I don't yet have the full explanation, the full proof. So, of course, it's impossible to apply Balaish more and more times. When the level grows, the computations, Balaish-like computations, become cumbersome and horrible and impossible. And even my not yet existing coworker could help a lot. Well, so I'm trying to do something very different. I tried recently last year, and let me start from another object. This time we are on the level 6. You see 6 letters, that is underlying dimension 8, but level 6 in the monster. And this class, this stratum, so again several R's, but also V's, not yet, not T yet. And this is local description to, say, Kumpera Ruiz generators. But the computation of nilpotent approximation has been done. And in fact, it is done in that reference, this paper from the year 2005. So this is the result. This is the result. Again, only 2 variables, observe this, only 2, Z1 and Z2 variables. And the respective weights are here. So these weights, of course, are closely related to this result and this computation presented in that journal paper, but is already quite complicated. What are these red weights will be clear in a moment. But I'm just mimicking the previous observation. You probably remember the very first example appeared closely related to the second, that in dimension in level 4 to the other at level 5. Namely, that extra variable Z1 helped us to conclude, to obtain the result that the second example is also not strongly nilpotent. Just the very particular appearance of Z1. So let me mimic that, but instead of writing Z1, let me introduce Z0 so as to keep the previous indices. Because previously you probably had some small trouble in locating, in identifying. Let me also, you see, this is the very first example, but with shift of indices. So this shift of indices is awkward, is cumbersome. So let's avoid shift of indices. Let's avoid, that is to say, let's introduce Z0 and keep the previous indices. And so I'm obtaining something that is possibly some nilpotent approximation, but I don't yet know that. In order to make it closer to be some nilpotent approximation of something, I'm just computing new weights, and these new weights, precisely those the red weights, are being computed starting or departing from this object and trying to preserve quasi-homogeneous weight -1. So this is that algebra or even arithmetic. So at each level, I'm trying to preserve quasi-homogeneous weight -1. This is that attempt of myself. And here is the resulting sequence of weights that you have seen already. Okay, so with weights, with new weights being these, simply it is immediate. What is small growth vector? Because small growth vector is being expressed by weights. This is just synonym to two synonymous weights of expression. So the small vector is this one. The sub-indices are just numbers of repetitions. Okay, so 2 4s, 2 5s, 4 6, etc. But having observed small vector, we know what is the underlying class or stratum. It is precisely this stratum. So the previous code that we started with, in fact, the journal 2005, with some extra letter B. This is being identified upon looking on the small vector. Okay, so probably this very object, or this very object, is probably the nilpotent approximation of this class, of this new class, being localized, identified upon looking on the small vector. So this is my conjecture, my working conjecture, and the next two slides probably are devoted to some functorial demonstration of that conjecture. In fact, it is true. My artificial construction, my very artificial construction, just mimicking the previous observation obtained, I repeat, by brute force and sound. And this is my conjectural mimicking of that way. And now I'm going forward. I'm just thinking that I have obtained the nilpotent approximation of this more longer, more complicated class. That is to say, of all points belonging, because that nilpotent approximation looks the same for all members of a given class of given stratum. I should have mentioned that earlier. So let me also compute this the square of that object that I suppose to be the proper object. So I'm computing the least square as previously, and the similar observation, and similarly as previously I'm obtaining, you see, well known the nilpotent approximation of the object present already in the paper 2005. So the outcome is that the big growth vector is of this kind. That is to say, is very bad. It's definitely not Goursat, and I'm on the good way to show non-equivalence. That is not strong nilpotency. So that technique that I'm going to propose is using Cartan prolongation, but my time, of course, is limited, so I'm going to skip to fly over these 2 pages. But the whole presentation, of course, I'm going to send to the organizers. So for those who would be interested, this will be available. So let me fly over the most important technical part. In fact, this is that improvement, that functoriality being applied to the whole stuff. Instead of using brute force of Belaïch, I'm using functoriality, using Cartan prolongation. And of course, it's not time to recall this very important notion of Cartan prolongation being present exactly in that paper of Elie Cartan 1914 and presented in modern form by Bryant and Xu, Robert Bryant and Lucas Xu, the important paper 1993 in Invenciones. So in fact, it is Cartan Bryant Xu prolongation that helps me to arrive at that conclusion that exactly this newer class is properly identified and is full of not strongly nilpotent points. So this is recapitulation of how this new ingredient in my arguments, and this is recapitulation of the previous, of the initial. So the very initial object that from the year 2000 and its prolongation by letter B. So from not strongly nilpotent to non-strongly nilpotent. And in more complicated situation, from not strongly nilpotent, think known from 2005, to not strongly nilpotent, something much more complicated, not really available by brute force already, because Belaïch would be too long, too complicated. But by functoriality, apparently available, this implication. So one more recapitulating the same. So I'm recapitulating now the same, so repeating, sorry for repetition. That initial object, not strongly nilpotent, that we know very well. That implied, as I tried to present, that the big growth vector of nilpotent approximation of the prolonged by letter B is bad, is not like the big growth vector of the initial. That is to say, of course, this object of all points of it, they are not strongly nilpotent. And the continuation of that recapitulation is here. So we started with this stratum full of not strongly nilpotent that we know from 17 years already. And we arrive at a continuation, some conclusion that continuing, prolonging it by letter P is again not strongly nilpotent. But this already by functoriality, remember. Okay, so let's try the last moments of my presentation. No letter T yet, and I promised to introduce that letter T. So to that second example, to that very initial, prolonged by V, so this not being strongly, now I'm prolonging by T, and using some similar observations, I'm arriving at a conclusion, similar conclusion that this, as you remember, this was not strongly, and prolonging this not strongly by letter T is again, yields again not strongly nilpotent. Of course, I'm not using brute force, but I'm using functoriality. And in fact, in these diagrams, in these pictures, a lot of functoriality is present, but I should pass over that by time consideration. Let me only mention that in case of T, that functoriality doesn't work so smoothly as in prolonging via letter P. That a lack of smoothness is indicated by this separating two blocks. So one should apply one small additional trick in order to remove that disadvantage, and having this presentation of the nilpotent approximation of this or candidate, it is easy to arrive that, okay, this is not only candidate, but truly a nilpotent approximation. It is. So here is the conclusion concerning that example with letter T. Let me skip the details because it is time to formulate the roadmap that I announced in the abstract. Yes. So these examples, and only examples, firstly presented by brute force, then by functoriality using Cartan prolongations, using the technology of Ophélie Cartan, improved in a sense by Robert Bryant. One is arriving at the following conjecture, still conjectural mode, but it is very plausible, and that functoriality should help in doing the full proof, but it is not yet done. Namely, which points are, in 2 minutes I'm going to finish, I hope, in 2 minutes. Which points in the Goursat monster tower, regardless of the length of the code, that is to say, regardless of the level in the monster, which points, which strata, because when a point is strongly, then then its strata is strong, and when not, then not. So let's think about words that end with some additional words, W, that end with R. They are auxiliary, they are not eventually. But so they end with R, but they do have some V inside. Not the single sequence of R's, that would be trivial. Something non-trivial inside, and the end by R. And let's continue with, let's complement that W by any entirely critical tail. Entirely critical means that it contains V's and T's, no R's. So again, W ends with R and contains inside V. And its prolongation, named U, is by an entirely critical tail, only V's and T's. So all such strata U, and only such strata, seem to be strongly nilpotent. And the reason for that is that the big growth vector in them is simply inherits the small growth vector of this beginning part. You see, this is the in conjectural mode the result and the main message of the presentation. So the huge, very long class, its nilpotent approximation. So apparently its big row vector is already encoded in this initial part that ends with R, the last R in the letter U. So because of that, such a class U is not strongly nilpotent. So I do hope of going through the details, but it is really conjectural mode for the time being. So recapitulation and the end of my talk is here. So what I'm striving to do, to perform, is to show that non-tangential is not strongly nilpotent. And when tangential implying strongly is very easy. And so to finish the last sentence, what is this tangential or not tangential? So any word that has some R after first V, so any word that has some letter R after some V is non-tangential. And tangential are classes that after the first V, so initially some R's, then V, and then no more R's, only entirely critical V's and T's. So these are tangentials. And such W continued, prolonged by V, is of course not tangential. So this is the state of affairs in the Goursat monster tower, and this is some recapitulation of the computations on the examples only. Well, thank you very much. Sorry for going over my time, but I started slightly later. Thank you for your attention.
Piotr, thank you very much. I think it's a very interesting talk. Please, any questions, comments, remarks? Piotr, may I ask you, with everything you do here, you are doing by hands, or you use some computer assistant or some maybe some.
Exactly, very good question. Yes, by hand, but of course my forces are limited, and Belaish algorithm forces are limited. So I'm looking for some new devices, and this functoriality based on Cartan prolongation technique is, it seems to me, the proper new device to omit the problems of hard computations, I hope.
Because it seems that here are only formal computations actually on the level of polynomials. Yes.
Yes.
And yes, maybe there are some packets, computer packets, programs which allows to do that.
Yes, Sergey, in case of your being aware of such packet, but such a packet should be focused on nilpotent Lie algebras with polynomial written vector fields. In case of your knowing something, please let me know. Of course, that wouldn't solve the entire my problem, but that would bring in much more examples, and I would of course feel much more at ease. In case of your knowing something, please indicate it.
That's very interesting, because it's just the idea of, there is a lot of things which are hidden on this tangency of high order.
Yes, yes.
Sure. But just one question. There is something like Loyasevich inequalities. Do you know? Is it related with this? Because
this is good question, but let me, despite the question being very good, the answer is, to my knowledge, not. Sorry for offering such an answer, but the Goursat monster tower is a very regular object. Let me just very briefly say that the levels, they are stratified. The levels of that horrible monster, they are stratified by strata encoded by those words over RVT. And the codimension of a given stratum is equal to the number of letters V and T. So as the only open dense stratum is RRR, only R's. And the number of V's and T's together gives you codimension. And this is very good stratification. Each level is so nicely stratified. It is that stratification satisfies all Whitney axioms or other axioms that you could invent.
It's like locally trivial, yes?
It is, yes, absolutely locally trivial. It is being described by the given stratum of a given codimension is being described by annihilation of several of Kumpera-Ruiz variables, simple. So it is no place to look for so sophisticated situations somehow related to Jasiewicz. But thanks for asking, and sorry for my answer being maybe disappointing at this point.
No, just asking. Okay. Piotr, thank you very much. Thank you. I'm very glad to meet you once again, and I hope that after our meeting we will meet personally. Thank
you very much. I also look very much forward, as Professor Telemann mentioned, to visiting in person Odessa and hoping for the best for your country. Okay, thank you again. Thank you.
Thank you very much. Thank you.